I had the calendar here for a reason. 2 announcements. Announcement number 1, which you'll enjoy, the 12th, week from today, I will not be planned absence day. I will likely be unavailable vis-a-vis getting online. I don't know I'm going to be online. I will likely record a presentation and send it with these YouTubes. I assume everybody's not had trouble opening them recently, the ones that know it's working, embedding them. If it's not, holler. I'll talk to the IT people. So you got plans that weekend and you can get out early, good. I know it's a 9 o'clock class, but I will not be here. Announcement number 2, somewhere. I'm thinking either here or here. Everybody starts at the first half. So, and the reason it's going to be week 5 is I think that's the lightest week you have for lab, based on the schedule. And I will confirm that. I'll get a chance to chat with Dr. Robbins either today or Monday and make sure that, what he has coming up. So I don't want to, the last thing you do is to have like a major practical going on in lab and have to be subject to exam. That's basically why we make sure we're doing all the lectures and all the labs. He does all the labs, I do all the lectures. Thanks. Jeez, hey. I know this is one of those when I was in college deals. Nobody gave it. I've got 3 exams this week. If you go into graduate levels or professional levels, nobody cares. This is your job, do it. But trying to be user friendly. Well, good. Let's begin. No side conversations, if you please, etc., etc. It's okay. Nevertheless, so we will start. Where am I here? I just wanted to reiterate because I didn't get more because I know I talked to you about. I just want to summarize it because maybe I did it kind of fast with these different things. Most of what you're going to talk about are solutions. Solutions, everything is dissolved. A myriad, a whole bunch of stuff is dissolved. You can see through them, and moreover, you can separate them. Okay, effectively, these are all different kinds of mixtures. And there's one that we haven't talked about that I'll get to at the end. And to understand, it's just important to understand that's what our body basically does. As we move, particles move because they're dissolved. It facilitates, it enables them to get through all those movement across membranes, whether they're sodiums or potassiums, and whether it's glucose, even though glucose, as you'll see, needs something in the membrane to enable it to do so. All of that stuff. That's the base. That's the backstory here. And the reason I'm racing through this a little bit is because I know I did it before. And inevitably, you guys get more in the morning. And then I get less and less because I keep adding stuff to the other 2 classes I do on Monday, Wednesdays, and Fridays. Colloids are interesting. And it's the big thing to underscore is effectively what it means. There's something in there that's holding on more or less to the water that's big enough that we can't see through it. And really, blood is both of these, a colloid and a suspension. I touched on it a little bit. Down the road, you're going to see as we get into physiology, particularly in the second half of the course, to understand this battle between your blood pressure pushing fluids and the proteins in your body holding on to fluids in the blood vessels. It's called colloid osmotic pressure, meaning it holds it in, pushes it out, so they're opposing forces. We keep them to a certain extent in balance, and it's subject to changes in the blood vessel structure. You get to that in blood vessels in lab, but that's in AP2. So it's a building block to understand. So blood has that role. And again, as long as the proteins are present and not faulty, they do this very well. You see, this becomes very evident when someone has liver disease. Because your liver makes all the proteins, basically. If your liver can't make them effectively, big trouble. And which leads us to what blood also is, and suspension is very straightforward. It's a combination of things, but as long as they're moving, it appears as they're relatively uniform. Like when you see a tube of blood that's taken out, most everybody's had one taken out somewhere by this time. Okay, there's nothing specific. You don't really see. Oh, it's a tube of blood. Not realizing that effectively, once it stops moving, things start to happen. And if you didn't know, in those little containers, they're called vacutainers. They have different colored tops. Some of them have nothing in them. Some of them have different chemicals, either making it clot, stopping it from clotting, all that type of stuff to do different tests. I mean, that's when people are lab techs and they go into it and they work in the lab. That's where they'll know. And the folks who are taking out your blood, if you go anywhere, they're all familiar with. They know from the orders. I got to have a blue top and a red top, and most, and I can tell you what they're for. It's purple top tube is for CBC. A red top tube is for something called a base metabolic panel, and it's kind of fun to talk about those. We're just getting you an idea, but once it stops moving, effectively what happens it will settle out. Again, we accelerate it by centrifugation, which is really all the blood bank does because it uses the parts differently. Very rarely do we transfuse whole blood. If a big, terrible accident, motor vehicle, bleeding internally, gunshot stabbers, bleeding externally, they get to the emergency room, then you use whole blood. But if you're most of the time when someone's getting a transfusion, they're getting what are called pack cells, which are the settled red blood cells. And those are there to, mostly for people who have very, very low blood counts, poor oxygen carrying capability. It's almost building them up, in order they can, particularly even vis-a-vis a surgery or replacing blood after a surgery. And that's little things, and I talk more about that in the blood unit. And again, I don't know if I'm doing AP2 yet or micro. I'll do one of the two. Maybe I'll do a mixture of both. I don't. So I'll tell you what I'm doing so you don't have to take me again. I would prefer it. Because I use the same old material, and you'll have heard all that stuff before. That was an opportunity to smile. I know it's early. Look. Good. And that's the last one of these that's here. I'll just tell you in passing is an emulsion. Effectively, an emulsion, you add an agent, and what it does, it basically it holds the suspension in such a way it doesn't settle out. So the next time you have ranch dressing, okay, it's an emulsion. If you make a creamy salad dressing or buy a creamy, it's an emulsion. Because you can sit in there in the fridge in that bottle, or if you make it yourself in whatever container, it doesn't separate until it gets very, very old, and then you probably know, pitch it. Okay. Remember Stein's motto: when in doubt, throw it out. It's a good model for food. That's an emulsion. Interestingly, our body uses things like that all the time in different areas. We use a magical chemical called lecithin, okay, which we have in utilizing in certain processes biochemically. Nothing my expert on that is she's teaching next door. She's a biochemistry professor. But we do cooking wise, you use mustard because lecithin. We use egg yolks when you make mayonnaise. Okay. That's where, and if you make, vegan mayonnaise, you use dry mustard and wet mustard. Just a little insight for cooking. Cooking's important. Yes, to watch the game, my son and I came over and got pizza. I know. I woke up this morning thankful that I am still alive in one of my survivor pools. Nobody watched the game this. First game of the season. You watched? Yeah, you watched? Yeah. Not an Eagles, as you could tell, but hey, at least I had the Eagles in this. Now we're hoping for Denver over the weekend. Always go with chalk in your survivor pool for the first week. You never know what's going to happen. Evident last night. Moving on. So again, what this is just sort of defines what they are, blah, blah, blah. The solutes. Again, the terms solute and solvent are very important. When I ask a question on an exam, it'll say the relationship of solutes to solvent, not water and stuff dissolved in the water. Okay? So understand you have to, and the reason I do that is you have to get used to using the appropriate terminology. You can explain it to each other if you're in a word about studying. I said it before, I will just reiterate it because I'm telling you the first time about the test. Don't think for 1 second that you can do this the night before. There's just going to be too much material. And the nature of the questions is more in depth. Okay, it's a mistake a lot of students make. I made those mistakes. Okay? Because I'm a smart kid from high school, going to college surrounded by a bunch of other smart kids, and finding out, oh, I could always study the night before and get A's. Happy dance, no, unhappy dance. I almost failed out. I mean, there were other reasons. Okay? This interesting time. We just had that Woodstock thing in 1969 before I matriculated. There's a lot of substances going on. I digress. Statute of limitations is expired. You can't get me. Okay, so solutions, mixtures, we're all about us. This is, okay, we do percent. Do we cover this? No, not yet. This is the start. In Chem Lab, we all had you had moles. Molarity and molality, you don't have to know that. One's concentration. Volume, I always have to know. But in biology, we do percent. So, this is roughly 0.9% sodium chloride salt solution. Down the road, you're going to learn that we call normal salt. I'm not going into why it's normal. What it means is, it means it's 0.9 grams salt in 100 milliliters of water. So percent comes from the 100 milliliters of water. That's what a deciliter is. Okay, hence the terms of percent. So now it's different. Most people know somebody uses a glucometer. They're diabetic, they got to test their blood sugar. So their blood sugar is going to say it's good today, 85. Okay, that's 85 grams percent. That's 85 grams of glucose. That's milligrams percent. That's milligrams percent. 85 milligrams of glucose, mg, sorry, the other one's percent, per 100 milliliters of blood. That's called blood glucose. There's also serum glucose, which we don't do anymore. It's just separate. And I talk about that when I do the blood unit. So again, it's just understand when you start seeing these things, they're not all the number. You have to know what the units are. Sometimes they're grams, sometimes they're milligrams. Now, I'm not going to ask you these, but for you going into clinical fields, someone's going to ask you those questions. First grade, apples and oranges, right? That first grade teacher with math units, oh, these are apples. They're not the same. Once you put them all together, how much stuff do you got? And this is, don't want to do it. I would remember this guy. I'm not going to ask you to repeat the number. When we give context to things, particularly when we get to a subject called pH, very shortly, that's the percentage of hydrogen ion concentration. It makes a lot more sense when you think about this. So Avogadro's numbers, 6.0, very famously 6.02 times 10 to 23rd. I don't remember the science behind it, despite my chemistry background. Effectively, in half an ounce of water, more or less, slightly more than a half an ounce of water, you have 6.02 times 10 to the 23rd molecules of water. It gives you an idea, 6 with 23 zeros, after just how tiny a molecule is that we're talking about. And that's why when we start talking about charge in water, why it adds up, why maybe you did it in high school. A lot of schools do it. They have like a light bulb and a dye, and like a little thing that can stick into a beaker of tap water, and all of a sudden it lights up. Did you ever do that experiment in school? There's enough charge going around the water to create a current that'll make the light bulb light. It's a typical, regular, old-fashioned incandescent light. And sometimes they had that set up when I was teaching CCAC years ago. Colloids, an emulsion and a colloid are not necessarily interchangeable. Okay, so I would say that. Again, different mixtures, et cetera, and really understand that the cytosol of a cell is when they talk about sol gel. It's a mixture of solution and things that are more gel-like, but depending on what's going on in them chemically, it varies. It's inconsistent. The interior of the cell is a very harsh environment. Okay, it has dramatic changes in concentration and pH. That's why membranes are so darn important. The membrane-bound organelles are little partitions. That's what membranes do. So what's happening on outside. I mean, it was pouring rain yesterday afternoon. Close the windows and and you're dry inside. So you're avoiding the changes in the external environment. That's what membranes do. And understand the interior of a cell is like that. That's where membrane-bound organelles come in. That's why. So it's the sophistication of the intracellular mechanism that's involved. Now here's a suspension. Water and sand. Mixtures do not involve chemical bonding. I'll buy that more or less. We can separate. We filter things all the time. Okay, coffee filter basically is a good example, even though it's not really a great example. That's the concept of filtration, and whether they're multiple particles or not. Homogeneous would suggest only one particle. Heterogeneous or heterogeneous, depending on how you pronounce it, would mean different kinds of particles. It's all leading up to this. These are energy relationships. It's very well stated. What we're going to explore the different kinds of bonds today. That's really the focal point of today's presentation. We have the remarkable ability in physics and in chemistry to be able to take electrons. When they pair together, they form a union that effectively holds energy. And as I said to you before, that's where we derive the energy for us to sort of more or less do business. So they're not physical structures, okay? And all of this determines all those variety of electrons that are in that outermost orbital. They're really the linchpin for all the chemical properties. And so here's the whole energy levels and blah, 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 how many they can have. And all you have to be concerned with, other than hydrogen and helium up there that have 2, all the others have 8. So when we start looking at, and really the next 2 rows, where we see, starting with lithium and sodium, and maybe the 3rd row with potassium, those are the ones that really involve molecules that we have a lot of contact with. And maybe iodine a little bit farther down. And you're going to see the ones that really impact us biologically as we talk about them. No, you do not have to remember. The table's going to be up there. I'll take a picture and print it. I was going to do that the other day. We'll get something for you. Because that's silly. We're not... Even when I took the MCATs, which are vastly different today, a very long time, they gave you a periodic table. So, it's an exercise in futility. So here's the valence shell, and understand what a valence electron is. The number of electrons that either have to be lost or gained to either empty or complete that shell. So sodium, lithium, potassium need to lose 1. Valence of 1. All the ones in that sort of pale, that light blue column over to the right, we call halogens, fluorine, chlorine, bromine, iodine, etc. All very nasty, by the way. And when we add those to things, you got to be careful with it, particularly consumables or things along those lines. Okay, they all have to gain 1. So their valence is 1. So the valence number is 1. The valence electrons are the electrons in that outermost orbital. Those are the definition that are there. And the whole idea of the 8s, and we talked about this before. And again, chemically inert. Remember, I made the distinction between physical properties and chemical properties. That's the kind of, and the biggest problem that students have when answering questions as they begin increasing degrees of difficulty is simple. They don't read the question. Sometimes the questions are very straightforward. A lot of times go back and read, and it's the hardest thing somebody does when they make up an exam is try not to give away the store, either in that question or another question. So there's always more information. And I mean, I just try it. I know somebody's going to do it in here. I'm not going to blame them. That's their style. They race out of here 15 minutes because I don't want to change any answers. Do me a favor, check it over. You mismark it. You don't want to change answers unless you misread it, mismarked it, or during the exam, all of a sudden you got a bolt from the blue and said, wait a minute, I remember we had a question about that. I'll go back and look at that. That's how it works. Dr. Robbins is much brighter than I am. Okay? I'm a great test taker. It's just the way it is. Everybody's got to have something they do well. Like I said, football, I can watch it with the best of them. Play it, forget it. It's a big fat kid with 280 pounds. All they do is put me in the middle of the line and say, "Lou, stand there. It'll be hard for them to get around you." Vertically, a half an inch. Just saying. So here we go. Hydrogen, one in the outermost shell. Beauty of carbon. Don't think carbon has to think three-dimensional. So the equal spacing is the beauty of the molecule. But it's not just equal like this. In one plane, you could take those electrons this way, that way, coming out at you, going backwards. They're all equally distributed. Remember when we looked at that cloud, and what made the cloud neutral when it was filled, like in helium, was the fact that they were sort of and that's what happens here. And the beauty of that with carbon is it means that it lends itself very nicely to what we call non-polar covalent bonds. Those are when electrons are shared equally. Those are the ones with the most energy. One molecule is pulling on one and tugging on the other. Oxygen, and you see, they write this a little bit differently. It's, again, we've been using these dot diagrams forever. I don't know if they're great. When it comes to oxygen, okay, oxygen's got 8 in the nucleus, just leave it at that, protons, not worry about the neutrons. Generally, in the old days, we wrote 2, 2, 2, and 2. The reality is, the distribution of the electrons when just the oxygen atom by itself, more like this. The unpaired electrons more frequently are close to each other than farther away. Okay, so they're not opposite each other. There is an imbalance in their distribution. Maybe that's the best way to express it. And that becomes relevant very soon. Here's sodium, all it wants to do as soon as possible. You never see, these days, you never see sodium isolated. Like I said, maybe I told you the story, buried in kerosene, chemistry, explosive. Historically, that was what they put into depth charges when they first made them in the Navy, more vis-a-vis World War I to combat submarines. And they were able to crank them in such a way, and when the seawater, to a pressure where the seawater, when it got deep enough, boom, sent them at 40 feet, sent them at 60 feet. And they don't use those anymore. Now you use destroyers use different weapons to get rid of that. I have a certain degree of knowledge about that. I'm privileged to report that for nearly a 2-year span, my eldest was the commanding officer of a guided missile destroyer. 3 major types of chemical bonds. So we're going to look at them. Ionic, 2 types of covalent, and the weakest bonds of all are as important as any biologically. Those are hydrogen bonds. So what's an ion? It's either gained or lost an electron. Number of protons does not equal number of electrons. Easy. It does. Stop with the transfer nonsense. Okay, it didn't happen. I told you, sodium is an explosive metal. Chlorine exists as a poison gas. An explosive metal and a poison gas didn't meet each other on the street and go, "I want your electron. Oh, please take my electron." And all of a sudden magically make table salt. It never happened. The sodium was already ionic sodium. The chloride was already ionic chloride. And then they met up and they had a magnetic attraction. That's what an ionic bond is. It's not sharing the electron. It's positive and negative attract. That's all it is. They attract. One becomes an anion, a negative ion. That's the way to remember it. Okay. Yeah, it gained an electron. And one becomes a cation. Just if you remember anion, the opposite is positive. I like the anion. That's what I learned. The negative. However it works for you. And that's what it is. And they show it to you. The same damn thing. Here's the sodium. Here's the chloride. Didn't happen that way. But here's how they form together. There's no tangible attachment And the beauty of that particular relationship is that it is so easy to separate. That's why they dissolve in water. So if you have something that also has positives and negatives, water, it can squeeze into that little gap, and all of a sudden it separates. So you're over here, the fluorides are over here. You stay there, you stay here. I was telling my colleagues this morning, I have to do that stuff. Keep you guys awake. Sorry. I'm in between belt knots. I keep picking up my clothes. That pizza did not help last night. Pizza IQ and Cranberry. Oh, they have a steak ranch pizza to die for. Good eats. Nevertheless, so they form salts, and they have their own characteristics. Salt has a distinct characteristic in the way it appears microscopically after the water is taken away. So that table salt that you could take the salt shaker, the little packet, wherever the cafeteria is these days, or the cafe, and take a look at it microscopically, and a lot of classes do that, you would see these neat little crystals that look like this. They're innocent. They're tiny little cubes or squares, that type of thing. They're geometrically not overly impressive. This is the way they appear. They're packed very tightly, but not so tightly that that teeny tiny molecule of water, remember how many there are in half an ounce, can sneak through there. All crystals are not created equal. You've heard of the disease, I would take it, called the gout. Okay? Gout is crystals. I make crystals called sodium urate. The crystals are like little daggers. They settle in joints and they punch. It's like they're inside of a joint in the foot, in the elbow, and they're so irritating. What your body does when it starts to irritate it, it sends white blood cells to gobble it up. Because of its shape, they can't gobble it up, and the white cells burst and they release more chemicals that are nasty. And I mean, all of a sudden it looks like hot foot or swollen, red hot swollen elbow. You swear it was an infection, but it's the gout. Okay? And if it's not treated properly, gout can be fatal. It has to take a long time. That's something we talk about a little bit when we talk about metabolic diseases like diabetes, in sort of the same family, but mostly because by a lack of an enzyme as opposed to diet, which they thought previously the diet contributes. Covalent bond, so that's simple. That whole idea, crystals are very, very interesting. They used it when we get to talk about DNA. It was the shape of those crystals that basically yielded the secret of DNA in the Watson and Crick model, and they didn't attribute it to the lady who actually discovered it, a lady named Rosalind Franklin, who unfortunately didn't get credit until she had died, which is an ongoing story about how women have always, in science and in medicine, have always not been recognized for their achievements. It is now beginning to change a little bit, thankfully. Covalent, sharing. You can share two. They're not, that's a single bond. That's when we start to look at these. You can share 4, 2 pairs. It's a double bond. That's what oxygen does. That's what carbon dioxide does. Okay, it's like, and I'm sure in high school you had those Tinker Toy models, the sticks and the balls, right? Look at, somebody had those models, didn't you, in school? Every chemistry class uses them. And that's really the idea of three-dimensionality. You can take that central carbon and move it all over the place. But when you had a double bond, you had like 2 little springs. And all of a sudden, I can't rotate it all the way around. Ringing a bell? Okay, yeah? That takes away what we call a degree of freedom. That becomes important about how it interacts. You will learn over time, biologically speaking, everything is about shape. Particularly when we get to proteins. Shape matters. And so you're going to see, this is where we get the discussion. So here's the class. If you're taking OChem, from my colleague, Dr. Badger, our department chair, and they're doing this right now, okay, they learn about the first organic compound. Organic, as you will come to know, is between carbon to carbon and carbon to hydrogen bonds. They are almost exclusively non-polar covalent. They're shared equally. So we take carbon and we bond it at each 4 spot. Understand again the three-dimensionality of it. Effectively, we create a cloud of electrons that at any one point in time are equally distributed. That's what makes it nonpolar. So when you have the carbon and a hydrogen here and a hydrogen here, wherever they're rotating three-dimensionally, they're evenly distributed. That's what makes a nonpolar covalent bond. The more you have of those in a molecule, the more likely it is to be lipid, read that as fat soluble. It's really important. That's the starting point. That's called methane. That's natural gas. Happens to be that, not that we're filled with natural gas, inevitably there are some, but really that's the start of understanding nonpolar covalent. And so eventually we break down things that we consume into a form where we can suck the energy out of this abundance of carbon to hydrogen bonds, whatever form they're in, fat soluble, water soluble, whatever. Okay? That's the resultant molecule. It happens to be a gas at room temperature. So here's oxygen. This is an example of here, and you can see what happened. It's almost biologically odd when you see something like that. You see the way they drew it here to make sense. It really happens. These two guys kind of get closer together, and another oxygen comes along, this and like this, and that creates a double bond. Why is that shape so important? It neatly sits on hemoglobin to allow us to basically survive, having oxygen. So the shape matters. Here's one that coming from car exhaust, coming from cigarette smoke. Unfortunately, how people try sometimes to do themselves in. Called carbon monoxide. It's very similar. It's a double bond. The trouble is, it sits on the hemoglobin much more sturdily. It attaches almost impossible to remove as opposed to oxygen. That's why smoke inhalation or fire, you're worried about carbon monoxide. With firefighters, that's a big problem. That's why when people close the garage door and figure they're done, that's what they do. And that's one of the things, that's why it's so hard to treat. If you don't get to them right away, it's almost impossible to do. Even pure oxygen, put them in an oxygen chair. That's what they do to try to, with firefighters, they do that frequently. There was a movie some time ago about that, Backdraft, but a while ago. If you're interested, it happened to be a really, really well-received movie. Just going on with that, and now we have nitrogen, triple bonds. And so here they're drawing it, thankfully they're doing away with all these, where the double bonds are located. Nitrogen has 3. And those are still covalent. We breathe oxygen and nitrogen. 80% nitrogen, roughly, 20% oxygen. That's what's it. We have some other trace gases and other stuff and water vapor in the air. That's it. So we have a lot of nitrogen. Nitrogen can cause problems, particularly for divers. They get a thing called the bends. We talk about that a little bit in respiration and why that occurs. So those are all equal sharing between the atoms, resulting in electrically balanced nonpolar, and CO2 would be a perfectly good example. Interestingly, this different shape, as opposed to the 2 oxygens, is why CO2, people were always erroneously taught, when oxygen is released from hemoglobin, the carbon dioxide is picked up and takes its place. It's like you gave it off your seat in the bus and the carbon dioxide. Doesn't happen. Most of the carbon dioxide happens to dissolve into the plasma. Some of it resides in what's called the globin. You'll get to that. Okay, interesting. So it was taught out of convenience, biologically, until we began to understand the process a little bit more. So you can see it's a different size molecule. That carbon monoxide has much more shape, is much more similar to oxygen, and therefore it turned out was even worse. The first, I hate to bring this up, the first Nazi death gas that was used was carbon monoxide. Buses that they basically reversed the exhaust into the bus. If you're interested for a little tragic World War II history. Polar is unequal sharing. Okay, so because of the different attracting ability to it. So you all know what water is. That's why when I draw the oxygen, I do it this way for a reason. We bring along a couple of hydrogens to the party. Hydrogen has a proton and one electron. I'm going to share here. Hydrogen has a proton and one electron. I'm going to share here. That's the way they shape when we analyze the shape and we have the capability here to do it. Looking at where the bond is. So hydrogen has a +1 charge. Oxygen has a +8. Carbon has a +6 charge, and these are all +1. Because of the shape, the structure, equally distributed, okay, what happens is those electrons at any one point in time are uniformly distributed. Not so with water. Water has that remarkable capability. Here, if I draw just the O's and the H's, I'll take away the bond and put a couple of electrons here and a couple of electrons here. Getting the other electrons that are still there, obviously, that +8, those +1s are unequally distributed shape-wise. So even in methane, the carbon is tugging on all of these, but because it's equal, the pull is equal in all directions, they basically oppose each other sufficiently so it stays the same. The charge is distributed uniformly. Everybody looking at that? What happens here is it's oxygen with the alkene. It pulls on those, pulls this guy, loosens this guy, loosens. So now we have in this molecule, if we just draw a circle around it, this becomes a little more negative. We just hold a couple of electrons to it. So we do this is the Greek letter delta looks like this in capital. Small looks like this. But it looks like this is partially negative. And because this side is partially negative, this side, the hydrogen side, is partially positive. So now we have, if you want to make the case, it's called a dipole. Partially positive, partially negative. That whole emulsions thing, that's because that lecithin or that mustard has one area that's partially positive and one partially negative. It creates something that one side of it is fat soluble and one side is water soluble. So water's a little bit different, but effectively we have a certain amount of irregular charge. So any now we get to the periodic table. The more you have of these four with hydrogen, oxygen and sulfur, nitrogen and phosphorus, similar. So the more OH, NH, PH, not pH, but pH, that's the base. So phosphorus and hydrogen bond, SH, both for hydrogen. The more of those you have, the more likely the molecule is water soluble. Was that equal distribution of charge creates a degree of polarity, degree of irregularity that makes this more compatible with water sweeping in between. I won't go through it. My chance to see what you're actually looking at. The replays from the game last night, pictures of your significant others, whatever. We didn't have those. We're sitting there with a stupid spiral notebook. Did the idiot ever stop talking? So, that unequal pull. We know there's a difference, +6 and +1, +8 and +1. Okay. It's how it's distributed. So the two different charges, dipole, fancy word. Here's that neat little thing. Positive, somewhat negative. That's partially negative and partially positive. And indeed, and because the hydrogens aren't at 90 degrees, as you might suspect, it's about 106 degrees. So even the positives are repelling each other. So the charge is easily scientifically verifiable. So in summary, all this is complete transfer. I hate that term. It's a magnetic attraction, easily separated. Not a strong bond, but an important one. Here, you have the unequal sharing, okay? Okay, and here you have the equal sharing. Fine. Hydrogen bonds. This is the magic. It's the magical thing about water. Why is water so important to us? Because of the hydrogen bonds. And so you have, this is a tiny, it's the weakest of all the bonds. It makes water a little more likely to stick next to each other. They're held together by this magnetic attraction, a weak magnetic attraction. And so it's liquid, and these intramolecular bonds hold that shape. They show it. I don't want to go through this here, but if we do this, you'll see. I'll make it look, maybe it look like it's knowing what it's doing. Yeah, we'll do it this way. Because I don't know if it's going to play sound with this until I check. I should have done that earlier. So voila, we draw these little dots. That indicates a hydrogen bond. Whenever you see that in your readings or on diagrams or in the book or on PowerPoints, that's a weak magnetic attraction. So how is that different? If I have those 6.02 times 10 to the 23rd water molecules, all weakly magnetically attracted to one another, and I have some type of oil, whatever, canola oil, don't use the EVOO, it costs too much. We use avocado oil at home, has a high smoke point. Do this simple experiment, and this is really where the properties of water that are so important biologically. Do not do this at home. Have 2 equal sized saucepans. Put, let's say it's a 4-quart pan, put a quart of water in one, put a quarter of the oil in the other. Turn the burners on equal, stick finger. Which finger are you pulling out first? The water one or the oil one? Which one's going to heat up the fastest? Pardon me? We have oil here. Did you say water? You said oil. And oil is a winner. Why is that? Because what makes oil, all those molecules, they're not attached to each other. They're not bonded. They just like to hang out together. And as soon as you start to heat it up, it increases their kinetic energy to start moving around. That's temperature. You're going to take your finger out of that real quick. As opposed to water, you've got to break those weak magnetic attractions. Why does ice float? Same deal. When we begin to cool it, these don't get shorter. So frozen water, ice, okay, is inherently a larger molecule than that. So when it comes together, those bonds elongate, and it actually makes it has more space, less density than water, than regular water underneath it when it's freezing. So it comes to the top. So just look, in the winter, pick a river around here. They had so much trouble with flooding around February that a lot of things have happened over the course of flooding with the Allegheny and the Yaak and the Ohio. The Army Corps of Engineers has come in various areas, put various things to keep what they call slush ice, because when it freezes over, watch out. All of a sudden that ice breaks, it all dams up together and little areas. I practiced in Venango County, Oilsey, Franklin, that area, Titusville, which is Crawford County, for many years. First 2 years, the whole downtown was flooded. What they did. And that was because of the confluence of the Allegheny, which is very large, and something called the Oil Creek, where they first discovered oil in this part, in Pennsylvania, actually in the continental United States. Drake's Well and all that. Because of that, surface tension, the molecules tend to adhere to each other. That's a water strider. Okay, it's not a bug that got lucky. Okay, this is it's the bug doesn't weigh a whole lot, but it's not, in that case, those tiny appendages were unable to break down those bonds that you were looking at before. And so that's why water is so forgiving. That whole homeostasis thing I about before. What was it talking about? Because when temperature goes up, it's going to take a while to break those bonds when your temperature goes down. It's like magically your blood is not magically all of a sudden starting to boil or starting to freeze. It doesn't happen. It's very forgiving. That's the magic of homeostasis. It's all about the water. So when you're dehydrated or you're overly hydrated, that's why it impacts homeostasis. We're nothing but big floating bags of water. Someone says it to me, it's hot air. Go ahead, you were thinking. Tell me somebody wasn't thinking that. You in the back were saying, I can tell. Back there, I can tell. So all the, okay. The whole reactants and products thing, don't even think of it. Because reactants, I don't even do that molecular and joined and unjoined. What you learned in basic chemistry is this. You get the idea, okay, anabolic, when we make something, we store energy in bonds. That's an anabolic reaction. Remember, we start off with catabolic and anabolic? If we break it apart, it's catabolic. We release energy because we're breaking apart the bond. But that suggests, that arrow suggests one way. Very little things in the body go in one way. They're reversible. Okay? Chemical reactions inside the body are almost, when it's irreversible, irreversible is a terrible word when you're in a medical field. What happened? This was damaged. Can we get it fixed? No, it's irreversible. Bad word. It's like treatable is a good word. Curable rarely exists. Irreversible damage is damage that you just don't want to hear about. So the question is how much the reactions, how easily they go from point backwards or forwards under certain circumstances. So I don't like it. So reactants and products, someone's going to ask you about them, and you'll remember it's reactants are here and products are there. Please don't, particularly if it's like a nursing instructor. Dr. Stein said it doesn't matter. Just say yes, okay. Believe me, I'm going to tell you a lot about those things. Just say, yeah, you're right. I got you. I know how to take yes for an answer. So when you put things together, we're storing energy in the bonds. We're making a protein. We're going to show you how to make proteins. Breaking them down, we're releasing energy, catabolic, decomposing it. You store sugar, and you have limited capability to store sugar in your body. Two places, liver, skeletal muscle. They're instant energy for emergencies. When we break them apart, they're all made out of glucose. So we're releasing that glucose, and the energy that's within there will be used as an energy resource. And yeah, we do a lot of this, flipping stuff around. I'll buy it. I don't go into this. A very important molecule. This is our energy currency. And what makes it important is we're constantly doing this. We're either breaking it apart to release energy or putting it back together to store energy. I didn't tell you, I'll just reiterate it. It's important. Whatever you weigh, you're making or breaking down that much every day. That's the equation we use the most in our body. It's such an interesting molecule. It's called the nucleotide. We will get into it. And what makes those high energy bonds high energy. And believe it or not, it's all about the charge. Those P's are called phosphates. They're negatively charged. Think kitchen magnets. I used to play with them, and sometimes they come together, sometimes you couldn't push them. Negatively charged, they repel. Forget it. I will not do this. I was a chemistry major. Just think of it. It's so counterintuitive. Oxidation means you lose electrons. Reduction means you gain electrons. Theoretically, it means because you're changing the charge. If you remember, oxidation loses an electron. Reduction is the opposite. I will not ask you any questions about redox reaction. I hated them in chemistry class. And we don't talk about heat. When it comes to energy, we now use the terms gonic, exergonic, give off. It used to be, when I learned about it, it was exothermic and endothermic. Somebody wrote a paper and they adopted it. I'm sorry. And that's really, I'm blabbing on endlessly with only 2 minutes left. I'll finish up the very tiny amount we have in this part, and we start the biochemistry on Monday. Thank you. Have a great weekend. 1 o'clock. Be watching. This is Steely Sunday.